We did Tudorson in detail, and also von Karman series in a bit of detail. So today we will just sketch the derivations of two other models. Hopefully we'll finish it at the next lecture. So hopefully we'll finish the theoretical modeling today, different ways of doing it. So last time we started what Schwarz did, 1940. It's basically the formulation of the thin airfoil theory. So you have your airfoil, something, any camber, whatever. So if you have your airfoil is moving with you, and this is angle of attack. So let me exaggerate this. So this is the U that the airfoil is moving by. So any point here in the airfoil is moving by this U. This is the angle of attack. From our thin airfoil theory stuff before, we assume circulation distribution, right? Gamma bound x, and we compute the velocity here at some point. So this vortex at a location, say x prime, this guy induces, or let's make it green, induces a velocity here at a location x, right? By the well-known relation gamma over 2 pi distance, and the distance is x minus x prime. This is at x prime, dx prime, and we will integrate if our units from negative b to b. This is the downward, or the downwash, right? The downward velocity due to this gamma. If we integrate, we get the total downwash at a location x. So this is negative because it's down. This is the flow velocity. This should equal to the velocity of the airfoil, right? Normal to the x-axis. The velocity of the airfoil was here simply, if you remember, this is at a particular location, say this guy. This angle is dz dx, and this whole angle is alpha. So this guy is negative u times alpha minus dz dx, if you remember. This is the thin airfoil theory. So in general, this is the v motion, positive upward, as a function of x. Correct? Okay? If you have any question, please stop me. So this was the exact same picture. We could have actually copied it from the thin airfoil theory, steady thin airfoil theory lecture. Now we're talking about unsteady. So what we should impose here to make this unsteady? So first of all, unsteady, we mean that this angle of attack is a function of time. Perhaps the u is also a function of time. So of course the strength of the circulation will also function of time. Okay? But if you just change things to be function of time, this is actually quasi-steady analysis. What do you need to account for in order to have an unsteady analysis? Wait. So I immediately have to extend this and have gamma wake of x and t. Okay? So I will have a very similar relation here, the almost exact same relation. Just distinguish that this is bound. I will have a very similar relation. So integral 2 pi x minus x prime gamma wake of x prime dx prime. But if the limits here from negative b to b, the limits over there will be from where? The limits in the red integral will be what? B to infinity. Very good. What is this equation represent? So it's this exact same thing now. This v motion is function of x and t. If I want to give a name for this, what is this? What does this equation represent? What does this equation represent? Is it your differential equation? Is it your boundary condition? Is it your, what's that? Is it the Cotta condition? What does this equation represent? What does this equation represent?
No penetration.
Exactly. This is the no penetration boundary condition. The normal velocity due of the flow is equal to the normal velocity due to motion, right? This is the no penetration boundary condition. So the formulation of Schwarz is very appealing. It's very simple. Okay, here is your formulation. We just added wake because it's unsteady, and we're applying the no penetration boundary condition. What is known and what is unknown in this equation? What is known? So the left hand side we have gamma bound, gamma wake. The right hand side we have v motion. So we have three things. Each is a function of x and t, which is given in these three variables and which is unknown. Which is given?
The right hand side.
Which is the v motion, exactly. Right hand side is known, right? And what is unknown?
Wake.
Both gamma bound and gamma wake. So we have two unknowns. Here we have two unknowns. This is an unknown and this is an unknown. So one equation and two unknowns, it doesn't work. We need a relation between gamma bound and gamma wake, which we started last time, right? So here we need a relation. I don't know what's happening with this pen. Between gamma bound and gamma wake, right? Last time we discussed what is a good candidate for this relation. What is a good candidate for this relation? If you need a relation between the bound circulation and the wake circulation, what is a good candidate for this relation?
Is there something to like we did last time?
Yeah, what was it? What's a good candidate for this relation? I mean, you can try to remember if you have a good memory, or just try to think. If I want to relate the bound circulation and the wake circulation, what is a good candidate?
The Kelvin condition.
The what?
The Kelvin condition.
Exactly, the law of zero total circulation, and they're almost equal and opposite, right? So yes, you can derive this relation either one of two ways, and we will take the two ways, discuss them. But I will not do all the details. I will just sketch the derivation, okay? Just to give you an idea how people can approach this kind of modeling. So if I start with zero circulation at the beginning, okay, whatever delta gamma occurs on the airfoil, I will have negative delta gamma on the other side, shed exactly from the trailing edge. So if I have here delta gamma change, which is gamma dot times dt, this will be associated with a shedding negative delta gamma at the trailing edge, right? Which is, because we have a distribution, can be represented as gamma wake at the trailing edge, right, and any t, times dz, okay? So this is, the pin is not sensitive. Okay? So these are equal and opposites. So this is equal to the negative of that. So right away you can get that gamma wake B and T dz dt is the speed, which is u, this is negative gamma dot at the same time. Very famous relation and heavily used in the airfoil theory. Unsteady force. Okay? Any question about that? We can get this relation using a different argument. Yes, Liam?
So for the gamma wave in red, it should be the other direction, right? In drawing.
Well, you find it, and this is the sense that we assumed it, right? And this term is based on this convention, and you can compute it. It's unknown, right? So we're gonna compute it at the end. Yes, and we expect that it will be the other way around if we're doing a step response, right? But if you're doing the harmonic anyway, it oscillates, right? Positive and negative. And this is function of x and t, function of x and t, right? Okay, another way of doing it, if you remember the unsteady Bernoulli equations. So this is here, it's here, what did we use here? What argument? We used the conservation of circulation, right? Conservation of circulation in an inviscid flow, and convection and assumption that the wake is free wake. What do we mean by free wake? We mean that the location of the wake vortex Z convects freely with the flow. And we assume that this convection velocity is u. So that dz dt, the speed of this vortex is simply u. Okay? So here we use these two arguments to come up with this very famous relation. If we start with the unsteady Bernoulli, and I will just try Bernoulli and you understand that this is the unsteady version of it. We already wrote this before. The delta P, the unsteady Bernoulli, was something like 2 rho, I guess, u times phi x plus phi t. This was our unsteady Bernoulli. And this is at any point. At any point, whether on the airfoil, this is unsteady Bernoulli, right? So this is delta P at any x, phi x at this location, phi t at this location. So what is phi x? What's phi x? What's partial phi partial x? Phi is the velocity potential. What's partial phi partial x? U is the velocity in the x direction. And from the airfoil theory, anybody remembers the relation between u and gamma?
Gamma over T.
Exactly, it's half gamma. Very good. The same here, we can do the same here. So actually phi t, so it's partial t for phi. And I want to write it in terms of u, so I will integrate over x, u dx, right? From negative b to any x. And again, u is half gamma. So you get immediately that delta p at any x is rho u gamma at this x, the distribution, plus rho partial t integral negative b to that x of gamma of whatever z dz. So this is another form of the unsteady Bernoulli equation that relates pressure not to velocity. I mean, Bernoulli is usually pressure to velocity. Then we managed to write it pressure to velocity potential. Here is pressure versus circulation distribution. Pressure versus vorticity or circulation distribution. Okay? Because we'll work with circulation. So because the wake convects freely, so at any point in the wake here, this delta pressure is the difference between the upper and lower surface. Here, if you integrate it, you get the lift force. Over there, how much do you expect delta pressure on this point? What is delta pressure here at any point in the wake? Over here, you have a solid surface that can sustain a force. Over there, there is nothing here. It's the same medium, right? So it cannot sustain a force. It's just the same medium. The pressure has to be continuous in this medium. So delta P here at any point in the wake, in particular, or any point in general, here, there, doesn't matter. Delta pressure is 0, right? So for any x greater than b in the wake, delta p is 0, implying, I will just divide by rho, implying what? That u gamma x plus, look at this, this is from negative b in the beginning of the airfoil until a point in the wake. So I will divide this integral because over the airfoil I have gamma bound, in the wake I have gamma wake. I will divide the integral. So the integral from negative b to b of gamma bound, what's that? What's the integral of negative b to b gamma bound? What's that? What is the integral of negative b to b gamma bound of x dx or z dz? What's that? What's this? Yes, the total bound circulation. I need partial t for that, so this is dot. Plus, so this is gamma wake now because I'm in the wake. Plus integration from b to x partial t gamma wake of z dz, right? Yeah. This is equal 0. This is the delta pressure. Okay, so this is what I did now. Simply one assumption is that it's free wake. It cannot sustain a force. Okay. Then the rest is very easy. I'll just differentiate this equation with respect to x. Let's do that. Let's differentiate this with respect to x, partial x. So you have u partial x, gamma wake of x and t, plus this guy is not function of x. This is the circulation over the airfoil. It's a global quantity. It's not local one. It's just function of time. Right? This is the total circulation of the airfoil. Partial x is 0. Here, if you have partial x, can cross the partial t. They are both independent variables. What is inside is not a function of x, it's a function of z. But we have one of the bounds. So apply, what's that? Leibniz. We apply Leibniz rule, okay? So basically, differentiate this with respect to x, which is 1 times evaluate this guy at the upper limit. Minus the same thing in the lower limit, but it's 0, because it doesn't depend on x. So when you differentiate this integral with respect to x and apply Leibniz, very straightforward, it's not fancy at all. You get partial t gamma wake at this x and t.